All right. So I'm not gonna hang around too long. If people join, they can join. I know Terry's so good to give us his time this evening that I don't want to keep him waiting for too long. So yeah, so I'm going to introduce tonight's speaker, Terry Moseley. And Terry, where do we start? I'm going to give a brief introduction, but
please,
you can fill in the blanks when you want to. But just to say, Terry's interest in astronomy, it took off in the 60s with his first homemade telescope. And that led him on to eventually getting access to the professional telescope up at Armagh Observatory. He's especially interested in observing Jupiter, Saturn, meteor showers, and eclipses of the moon, and particularly the sun. And he's just back from Australia, where he was lucky enough to observe some of that. And then some of that, Terry's accolades include he's a fellow of the British Astronomical Association and the Royal Astronomical Association, easy for me to say. He's also been elected the president of the Irish Astronomical Association a record 4 times. He was honoured to receive the Queen's British Empire Medal for outreach in astronomy, and he's even had an asteroid named after him by the International Astronomical Union. So if you want to look it up, it's 16693 Moseley. But from our own perspective, we'd just like to thank you, Terry, for your long-standing support for the club, but also for the festival and all the events that you've attended throughout the years. So without further ado, I'd just like to welcome Terry for tonight's talk. I'm going to hand it over to you now. Thanks a lot, Terry.
Okay. Thanks very much. Can you hear me?
Loud and clear, yeah. So
right, I just got a message on the screen, failed to detect your audio device, which was not good. Right, let me go. First of all, thanks very much for asking me, and I'm happy enough to do this by Zoom, but I'm just sorry I can't be there in beautiful County Mayo with you. As you know, I love the area, go to all your dark sky events and so on, and before that I used to go regularly on holiday there to Achill and so on, one of my favourite places on the planet. So anyway, yes, thanks for that intro. I'm going to now try and share screen, and let's hope this will work. Right, okay, folks, okay. Sorry about that. It's, we've had worse IT problems with that in Queen's University, where they're supposed to have the state-of-the-art facilities. Anyway, thank you all for joining, and sorry about that. I hope I haven't held you back too hard. Right, I'll not go into the background as to how this talk came about. I'll go straight into it. The tides basically are astronomical, and anybody with a bit of an interest in astronomy knows basically that the sun and the moon cause the tides, but there's a lot more to it than that. So let's get into the talk. They are extremely well known from ancient times, since people first started sailing, basically, I suppose, in the Mediterranean and the Persian Gulf and that sort of area. And they occur a lot in literature, and your local pirate queen, if you go down to the bottom, would have been very, very well acquainted with the local tides. And one story that I look at, apparently this is true. King Canute, about a millennium ago, had a bunch of acolytes who were so convinced and were just sucking up to him, basically said that his powers were divine and he could do anything he wanted to do. So to show with a rare example of divine or kingly modesty, he proved that he couldn't. He took the throne down to the beach, sat in it, and repeatedly commanded the tide not to come in. But of course, the tide totally ignored him. So I think that is actually a true story. So yeah, the tides are basically fundamental to anybody that has anything to do with the sea. And before the advent of air travel, basically any travel anywhere around the world from one country to another, unless they were adjoining on land, involved a sea journey. Trade, bringing stuff from the rest of the world to your particular country for, you know, importing anything from bananas to sheep from Australia, or sending sheep to Australia, whatever. It was all done by sea, and the tides were fundamental to that. So what causes them? And basically it's our old friend gravity. And a lot of you will know this, but maybe not everybody will know all the details. It's the pull of the sun's gravity that makes the Earth orbit the sun, and the pull of the Earth's gravity that makes the moon orbit the Earth. But importantly, gravity works both ways. And the Earth also has a very small gravitational pull on the sun, and the moon also has a small but a significant gravitational pull on the Earth, and we'll come on to that later. It's quite important. So Newton put it very simply: every body in the universe attracts every other body with a force varying directly as the product of the masses and inversely as the square of the distance between them. So it's a direct relationship between the masses, but it's a squared relationship with distance, which means that the closer two bodies are together, the stronger the pull by a factor which is more than the factor of the mass of the bodies. So as the moon is much closer to Earth than the sun, its gravitational pull on the Earth is about twice as strong as that of the sun, although obviously its mass is a lot less. Now, as I say, both are involved, but I'm going to deal here mainly with the effect of the moon. It's the most interesting and it causes the greatest variations. So putting that just in a diagrammatic form, the Earth is about 81 times more massive than the moon, and they therefore don't revolve around, the moon does not revolve around the Earth. The Earth and the moon revolve around their common center of gravity called the barycenter. That is actually located within the Earth, but not at the center of the Earth. It's about 3,000 miles roughly from the center of the Earth, and the Earth radius is approximately 4,000 miles. So every month, basically, the Earth wobbles around the moon with a radius of approximately 3,000 miles around the barycenter. And if you're calculating anything to do with the moon accurately, you need to allow for that. The other thing is that the pull of the Earth's gravity over the billions of years has kept the moon tidally locked. There's been a pull on the moon, and although the moon has no water, the bulge in the moon, the pull of the Earth, has actually distorted the moon very slightly so that it's egg-shaped, and one of the ends of the egg is permanently pointing towards the Earth because of the gravitational pull of the Earth. And that's why we only see at any one time and one side of the moon. There's effects called libration, which I'm not going to go into here, which allows us to see a little bit more top and bottom, left and right, due to the variations in its orbital speed. So the next question that people might ask is, if the moon is pulling on the water in the Earth's oceans, and the moon is up and it goes around the Earth approximately once a day, we'll go into that a bit more detail later, why are there two high tides every day instead of just one? And the answer is very simple. On the side facing the moon's pull, the gravitational pull, is stronger, and therefore it pulls the waters in the ocean towards it there. But on the far side of the Earth, the moon's gravitational pull is therefore that much weaker, and therefore there is less gravitational pull from the moon on the far side of the Earth, and therefore the water can escape a little bit further away from the moon. And in between the two high tides, you obviously have the two low tides. So two high tides every day, and we'll look at the approximately bit as we go on. So that is more or less what I was saying there. At the moment, the water on the far side of the moon still feels the gravity from the Earth, but there's a reduced pull of the gravity from the moon because it's further away from that point, and the water therefore feels less gravity, and it can escape further away from the pull of the moon. The Earth, of course, spins on its axis once every day, and it rotates under those tidal bulges, experiencing two tides and two low tides every day, again, approximately. So why are there not exactly two tides per day? So the Earth, as we know, rotates once every 24 hours. And if the moon wasn't moving in its orbit, we would have exactly two high tides and two low tides every 24 hours. But of course, the moon is moving around the Earth as well, once every 29.5 days, which is new moon to new moon, from west to east. So at any given time, any place on the Earth's surface has to move around a little bit more each day to catch up with the direction to the moon. So can you see my mouse? Can you see the mouse moving? Yeah. So the moon is moving around like that once a month, and we'll look at this in a bit more detail later. Sorry, I was losing my track of thought there. Yeah, the Earth has to spin round a little bit more, about 25 minutes in between two high tides or two low tides for the direction to the moon to catch up with the direction of the pull. So, since both the sun and the moon pull on the Earth, they cause the tides, but the moon is closer and its effect is greater. However, the sun still very much has an effect. So at new moon and full moon, whenever they're all lined up, the pull from the sun and the moon add together to each other, and we get an even higher tide called a spring tide. Nothing to do with the season of the spring. It's a different meaning to the word spring, if you like. It springs up higher, if you like. And they can be twice as high and twice as low, because the higher the tide at high tide, the lower the tide at low tide. In between, you get what's called a neap tide, whenever the sun and the moon are pulling at right angles to each other. And that is when the tidal range is least. It's not the actual height of the tide, it's the range of the tide from low to high. So a spring tide is very, very low when it's a low tide, and it's very high when it's a high tide. And it's in between at a neap tide. In other words, the high tide isn't quite so high and the low tide isn't quite so low. And for anybody involved with sailing or boats or anything, they would be aware of that. But again, there's more to it even than that. So looking at that again with a diagram, there you have the gravitational pull of the sun to the left and the gravitational pull of the moon upwards in this case. So the two pulls are at right angles to each other, and the pull from the sun partially cancels out the effect of the pull from the moon. So that gives you a neap tide when it's the tidal range is not as high as at a spring tide. High tide won't be as high, and low tide won't be as low. And you probably are reasonably well aware of that around Newport, where you have the sea coming into the bay there. Now, there's a lot more to that as well, particularly at spring tides. You have a much greater volume of water, which has to move up and down or in and out along coastlines and estuaries over the same period of time. And that means that tidal currents are much stronger during spring tides and neap tides. One that we're quite familiar with here is at the mouth of Strangford Lough. You may not know the geography of Ireland all that well, but that's Belfast there. There's the lough, and there are what's called the Strangford Narrows there. And all the water in that lough goes in and out with every tide. And the current there can be up to 10 knots, which is more than you would manage, certainly in a rowing boat or a canoe or anything. So you have to be very, very careful. And just some of the effects there, that shows the flow downstream of what a tidal power generator that was put in there on a trial basis. So you can see that's just like the flow from a river, extremely fast. And in your own area, the Bull's Mouth up on the northeast corner of Achill, or the Channel near Bellicracker, which is north of Mulranny, you have a reasonable amount of water going through a fairly narrow gap, and you will see quite fast tidal races there. And I'm sure anybody that does any sailing in that area will be well aware of that. You could very easily be carried along faster than you can move your boat with that power. So it's something to be very much aware of. Now, another question that an awful lot of people ask is, whenever there's a high tide, does that coincide with the full moon being up in the sky? In other words, if it was clear tonight, it's not here, the moon is coming up to full. If the moon was overhead, over where you are, would that mean that it would also be high tide at that particular time? Well, the answer is no, it's not as simple as that. The same would apply at new moon, which would be in line with the sun. And if the sun was high up in the sky, again, would that tell you that there's a high tide locally? Well, there's two effects, and we're going to look at one of them just at this stage: tidal friction. as the Earth spins, the tides wash up against the shore of all the continents and islands on the Earth, and that actually slows down the progress of the tides. So the Earth is rotating from west to east, like that from there. Oh, sorry, let's go back. If I click the mouse there, the wrong thing happens. From, in this diagram, say from America over towards Europe, as the tide reaches the coast of Europe and Africa, it literally is slowed down by the interaction with the coastline. And that slows down the progress of the tides relative to the moon. So there's always a time lag which varies locally between the moon passing over and the next high tide. It will occur, obviously within about 6 hours, otherwise things would get totally out of step. There's another factor as well, which I'm going to come on to later, but just to look at something that affects the height of the tide. Everybody, I think, listening into this will know that the moon moves higher and lower in the sky. It follows roughly the same path around the sky as the sun. So the sun is high up at this time of year, low down in the middle of the winter. Full moon is obviously opposite to that. So the full moon in summer is low down because it's 180 degrees along the ecliptic, and vice versa. In the middle of the winter, when the sun is low down, the full moon will be high up. But it can also go more than 5 degrees further north and further south than the sun, because its orbit is tilted at an angle of over 5 degrees to that of our orbit around the sun. So at our latitude, at roughly 54 degrees north, the moon can go up to about 59, a bit over 59 degrees north. And at the other extreme, when the sun's only about, guessing about 15 degrees below the horizon from our latitude in the middle of winter, the moon can go 5 degrees further to the south than that. So just look at one particular example of that. If the moon is high up in the sky, instead of the pull being mainly along the line of the equator, it'll be in the line towards where we are at, say, 54 degrees north. So we will then get a higher tide at the high tide and a lower tide of the low tide than somebody on the equator, because that's the direction to the equator, and that's the direction approximately to the direction that we would be at 54 degrees north. So the altitude of the moon in the sky, in particular its declination, which is the term that astronomers use to represent its distance north or south of the celestial equator, that can give you an extra large high tide and an extra small high tide, depending on where you are. Now, another factor, of course, is the distance of the moon, and anybody that follows the hype in the media about supermoons and mini-moons and all the rest of it will be well aware of this. The distance of the moon from the Earth varies. It's not a circle. It's what's called an ellipse, and the eccentricity of 5.4%. In other words, that's the variation from circularity. So the distance from us varies quite considerably, 356,000 kilometers roughly to 407,000 kilometers roughly at apogee. Those are extreme values, and the normal perigee and apogee distance of the moon are not always quite as much as those, but say roughly 350,000 kilometers at its closest and roughly 400,000 kilometers at its most distant. And remember that the pull varies with the square of the distance. So that amount of variation in distance is quite significant. So the pull of the moon at perigee is a good bit stronger than when it's at apogee. And if it's a perigee moon, or what the astrologers and the media call a supermoon and a full moon at the same time, then the tidal range will be correspondingly higher. Remember, it's not just that the high tide is high, the low tide will also be low, because think of it this way, all the water that is going to cause a very high tide at one part of the Earth is being taken away, if you like, from the rest of the ocean at 90 degrees around the Earth. So the low tide will be a lot lower, as well as the high tide being a bit higher. Now, this is where things start to get a bit technical and complicated. The period between the perigee and the apogee, in other words, the very close moon and the very distant moon, doesn't coincide with the interval between full moons. So they gradually slip into and out of phase. Sometimes sometimes the moon occurs with perigee and sometimes with apogee and others in between. You can see there the figures. The average interval between new moons is roughly 29.5 days, and the interval between successive perigees is roughly 27.5 days. So they gradually work into phase and then gradually work out of phase again. There are also very important topographical factors. The tides, if you think of, for example, trying to be politically correct, these islands rather than the British Isles, the tides have to work their way around the islands, and that gives you some idea of the complexity of the motion of the tides and the time delay that it takes for the tides to work their way around. You have a very, very simple situation there on the west coast. The tide will simply come into the bay at Newport, high tide, and 6 hours later, roughly, it'll be out again at low tide. But if you think of the same effect of the water trying to get round the North Channel there between Northern Ireland and Scotland, or there between roughly Wexford and Wales and so on, extremely complicated, and it causes a time delay of many hours sometimes, and you get the same sort of effect obviously in the English Channel and so on. So on a smaller scale, if you think of Lough Swilly up in Donegal or the Shannon Estuary, the tides also have to work their way into the estuaries and lochs, and that also causes a time delay. They get slowed down if they move over shallows and sandbars compared with moving in deep channels. And also a strong wind can either slow down the effect of the tide if it's blowing with the tide coming in, or speed it up if it's speed it up if it's coming with the motion of the tide, or vice versa. So that affects timing and heights of tides according to location. The highest tide I ever experienced locally, when my friends and I owned a cottage up in County Donegal, was when there was a strong wind blowing in off the Atlantic, coinciding with a perigee moon, and the moon was full. And also there was an extremely low pressure area, which I'm going to mention in a moment. And that caused that high tide to be at least 2 feet higher than the normal maximum range of a high tide in that area. So, as I said a moment ago, there's also a considerable delay in the effect of the tides. If you again look at, say, in the Irish Sea, where the effect of the tide has to work its way either south up through St. George's Channel or down through the North Channel, and then they meet. I think that's roughly the area where the two tidal surges meet. So it can be extremely complicated, and I think working out the tides at Dublin is one of the most awkward things for people to work out because of the variation. Right. So this is a very interesting aspect, and it's of more interest to astronomers than it is necessarily to sailors. So tidal friction, as we mentioned, gradually slows down the Earth's spin rate. So that is something that should be of interest to us all. And this is where the other effect in terms of the tide not coinciding with the moon or the sun being overhead, the spin of the Earth carries the tidal bulge ahead of the Earth-Moon line, because the Earth spins once every 24 hours, whereas the moon takes 29.5 days to go right around the Earth. So as the Earth is spinning, the friction actually carries the bulge of the tides round ahead of the direction between the Earth and the moon. And that offset then has two effects. First of all, as I say, it's slowing down the rotation just because of the tidal friction. But as I said at the beginning, not only is the Earth pulling on the moon is also pulling back on the Earth. And so that bulge of water there, the moon is trying to pull it back towards it. Okay, you can't escape the gravity. The gravity works both ways. The moon is pulling on the Earth, and it pulls also in particular on the bulge of water that's caused by the tide causing more water in that area. So the moon is trying to pull that bulge of water back, and the tidal friction also works in the opposite direction. So that is basically what is causing this, the rotation of the Earth to slow down very, very slightly, but measurable. Now, you may have heard of leap seconds, which are added at intervals to keep the Earth's actual rotation time in sync with what everybody uses now, from your computer to aircraft landing and time zones or whatever, a constant atomic time. So if the Earth is slowing down now, that means in the distant past it must have rotated faster, because the slowing down has been progressive. And hundreds of millions of years ago, our day was actually only about 22 hours long. And going back even further than that, it would have been shorter still. The thing is, we can't really calculate exactly how it worked, because there are a whole lot of other factors, such as for example, in the distant past, the Earth had just one giant continent, Gondwana land. So there wasn't the whole plethora of different coasts that we have along, say, for example, the coast of the Americas, the coast of Africa and Europe, the coast of Asia, just one big continent. So the tidal friction was less. But we know for a fact that the Earth's rotation, going back to as far as when the Earth actually had liquid water for that tidal effect, that the Earth would have been spinning a lot faster then. So the current rate of increase is only about 1.8 milliseconds every century in terms of the increase of the length of a day, which is very, very slight, but it builds up. There's other effects as well, which means that it's not exactly 1.8 milliseconds every century, but well, I'll mention some of those effects later on. But there's another effect to that as well. And that brings us to another fundamental physical principle called the conservation of angular momentum. Or as Scotty would have said in Star Trek, you can't change the laws of physics, Captain. So the angular momentum of the whole Earth-Moon system has to be conserved. That is a fundamental law of physics. As the Earth is slowing down, its angular momentum, part of the angular momentum of the Earth, is simply the fact that it is spinning. It would take a lot of energy to stop the Earth spinning, think of it that way. So the angular momentum is being transferred to the Moon by pulling it further ahead in its orbit. Okay, the bulge, as I mentioned before, is being pulled back to the Moon, and that makes the Earth slow down. But conversely, that bulge is also pulling in that direction to pull the Moon faster in its orbit. And how is that then making the Moon slow down? Well, by conserving the effect of conserving the angular momentum is that the Moon actually moves further away from the Earth, and therefore it's describing a bigger orbit. It's moving more slowly, but because it's further away, that conserves the total angular momentum within the Earth-Moon system. And that means that then in the future, the tides are going to give us both longer days because of the slowing down of the Earth's spin, and longer months because the Moon will be further away, and therefore it will take longer to orbit the Earth. And we know that slowing is real. If we look back at reports of where ancient solar eclipses occurred and when they occurred, and we apply sort of a constant 24-hour day and work back several thousand years, you don't get an eclipse happening where the local reports said it did. So we know it's an actual effect. Now, in the longer term, the further the Moon moves away from the Earth, obviously the effect of the tides will lessen. Remember the inverse square law. So the slowing effect will gradually lessen, but it won't actually stop. There are other things like, for example, tectonic movements. And we're talking here about periods of tens of millions of years. For example, at the moment, the North American plate containing the whole of the continent of North America is moving away from the European plate, and the Atlantic Ocean is actually widening. In the longer term, there'll be other much bigger effects, and that means that the effect of the tides washing up against the shorelines will change because the shorelines will change. So it's very difficult to predict when, but certainly in billions of years, the day will have lengthened so much that it's the same length as the month. Even though the month is lengthening, the Earth's day will lengthen more quickly, if you like, and the Earth will become tidally locked to the moon. And it will always appear in the sky over the same part of the Earth, just as if you're standing on the moon, you'll always see the Earth more or less in the same part of the sky above your head. It varies slightly because of libration, but in general terms, that's what will happen. And another effect is that in many millions of years, the moon will have got so far away that its apparent diameter will shrunk, and it will never appear big enough to give a total solar eclipse. All eclipses will be annular, and as the moon moves further and further away, they'll become more like a transit than an eclipse. In other words, the moon might be only about a quarter of the apparent diameter of the sun, instead of being approximately the same diameter as it is at the moment. Now, there are a whole lot of other things that tides cause. Anybody that's interested in astronomy has probably heard of variable stars and novae in particular. And starting at a sort of a smaller version of those, we have things called dwarf novae and recurrent novae. T Corona Borealis, called the Blaze Star, that it is there. There it is there, sorry, in the constellation of Corona, the Northern Crown. We'll ignore R, which is another type of variable star there. So that star there is normally about 10th magnitude, but several times in recorded history, it has gone into an explosive outburst, and at its very brightest, it has become as bright as 2nd magnitude, which would make it almost as bright as Alpha there in the Northern Crown Corona Borealis. And an ordinary nova, which is the ones that are the most spectacular, like that one there, which I remember well, Nova Cygni in 1975, became almost as bright as Deneb. There's the constellation of the Swan, or the Northern Cross there. There's Deneb, the brightest star. Nova Cygni became almost as bright as Deneb, so it made a significant difference to the appearance of the sky. And that's, both those are caused by tides, but not tides with water, tides in the stars themselves. Sorry, I've gone a wee bit too far there. Whoops. I thought I had a slide which actually illustrated it, but basically what's happening is, in each of those cases, you have a binary star system, two stars revolving around each other. And the tidal pull of the denser star, which may, not always, but sometimes may be a white dwarf, pulls material off its neighbor. And when enough material has been pulled off onto what we call an accretion disk surrounding the star, it piles up, and there's enough of it there to start a mini nuclear explosion. And that's what causes the brightening of the star. So T Corona Borealis there can go from 10th magnitude up to about 2nd magnitude. The last explosion was in 1946. They happen every 70 to 80 years on average. So we are overdue another one. So whenever you get a chance to look at the sky, I think most people will probably know Corona Borealis. Look there, count from Alpha, 1, 2, 3, 4, and then approximately at right angles down that way. If you see a bright star there, it means that T Corona has had an accumulation of tidal material from its companion, which has gone into an explosion. The same thing happens with what we call a classical nova, except that's on a much bigger scale. And of course, on an even larger scale, we get what we call type 1a supernovae, which are extremely important in astronomy. They're what allow us to measure distances out to the far edges of the universe, basically. And there you have, it's a different, same principle, but a different scenario. A star which is pulling material off its surrounding star. You can see that there's been actually a disk there. So that's a small dense star. That's a red giant or a red supergiant. It's very distended. The outer atmosphere is a long way from the center of the star, so it's not being held on so tightly. The gravitational pull from that, which would be a white dwarf, is much stronger because it's a denser object, and the material gets pulled off into an accretion disk surrounding the star. And whenever a certain amount has accumulated, it goes supernova. It starts an explosive nuclear reaction, and the star can increase in brightness by a factor of 12 to 15 magnitudes. Now, the important thing about that, as far as the distance scale is concerned, is that as far as we can tell, it always takes the same amount of matter to have accumulated on the accretion disk before it explodes. And therefore, with qualifications, which I'm not going to go into, allowing for slight variations in the type of the star, a type 1A supernova always reaches the same maximum brightness. And therefore, if you measure the apparent brightness of the star when it explodes, you can work out how far away it is. Obviously, the further away, the fainter it appears. And then we've discovered recently, and this was sort of the fundamental stuff in the latest episode of Astronomy, gravitational waves, where you have two black holes colliding, or a neutron star colliding with a black hole, or drawing material off from the surrounding companion onto the black hole. And that gives us what we call a tidal disruption event. And the same principle, the actual physics are different, but basically the material gets pulled onto an accretion disk surrounding the black hole in this particular example. And again, when a sufficient amount of that has been pulled onto the accretion disk, it explodes. And in extreme cases, we can detect gravitational waves whenever that sort of event happens. Another very interesting aspect is that tides may make life possible on two of the outer solar system moons, Europa, one of the moons of Jupiter, and Enceladus, one of the moons of Saturn. And the principles are the same. I'll talk mainly about Enceladus. Now, this diagram is exaggerated very considerably, but there's the planet Saturn. There's Enceladus, which is slightly egg-shaped. And as it moves around in its elliptical orbit, the point pointing directly towards the planet shifts because of the varying speed of motion around the planet. The same sort of effect that causes the libration of the moon. So on that point there, the pull is exactly along the long axis of the moon. Remember, this is very exaggerated, but there the pull has been shifted against at an angle relative to the long axis. And it's an effect that you get similar to if you take a rubber ball and squeeze it in your hand like that, it will heat up. The tidal effect of the squeezing in one direction and then in another direction is enough to cause internal heating. And therefore, even though Enceladus is away out at the orbit of Saturn, there's enough heat coming from that tidal squeezing, friction, if you like, compression and relaxation to make the water under the icy crust liquid. And also the tidal effects mean that the surface of Enceladus ruptures every so often, and we get these what are called tiger stripes, where the surface is cracking. And where the surface cracks, in extreme cases, the material actually vents out through the cracks into space. And there's an actual photograph of it. And some of the spacecraft have flown through those plumes of that's basically water material, water ice. As soon as it gets out into the coldest space, it instantly freezes. So that those are little ice droplets, or ice crystals, I should say. They've sampled those, and also they look at them with spectroscopes and so on. And the latest thing that actually has been detected just within the last week is that in Enceladus, they have now discovered the last of what we call the elements that are essential for life, phosphorus. It has been the hardest to detect. The other ones like oxygen, hydrogen, carbon, and so on had been detected relatively easily. Phosphorus was tricky, partly because there's less of it, but they have now detected it within these icy plumes emanating from Enceladus. We think it would be the same situation on Europa. So the fascinating thing is, in those liquid oceans below the icy surface of those moons, there are all the essential elements for life, liquid water and the essential elements. And there's quite a degree of confidence that there is some form of very primitive life existing below the icy surfaces of those moons. And there's a mission on its way out there, JUICE, the Jupiter Icy Moons Explorer, which is going to obviously go to Jupiter, and therefore it'll be looking at Europa to try and find out more. In the longer term, they're talking about sending a probe to either one of Europa or Enceladus onto the surface, possibly to try and burrow down into one of the cracks and actually sample down below where the water is liquid and see if there's any form of life there. So tides have amazing effects, as well as just giving us the high tides and the low tides on Earth. There are other effects. I tried to get a video of this, but I couldn't get it to run. This is the largest tidal bore on Earth on the Shanquang River, I think it is, in China. I saw that when I was out there for a previous solar eclipse expedition. And obviously, with its total solar eclipse, the moon was new. Therefore, you got a high tide, and therefore a spring tide and a very high tide. And you can see the shoreline away in the distance there. This tidal bore, where the tide is going against the flow of the river out towards the sea, and the particular circumstances causes this advance of the tidal water coming in. And sometimes, particularly in the Severn estuary and near Bristol, there's a tidal bore there which is not so strong, and people surf it for miles and miles up the estuary. I think that one there is so violent that nobody dares surf it, and every so often people have actually been drowned by it because it washes up so high, sometimes along the shoreline, that people are swept away. So it's something you need to treat with respect. And tides, of course, catch even the ordinary person like me, this isn't me, by the way, a landlubber by surprise. You drive down onto a nice beach and you leave the car, and you maybe have a few glasses of wine along with your picnic, and you fall asleep, and the next minute the tide has come in and there's your car soaked. Or you tie up your boat on the quayside when the tide is high, and you don't leave enough room on the rope, and as the tide goes out, the boat is left hanging there. Now, believe it or not, that is the only photograph I could find on the internet of that happening. And yet I saw for myself up in Donegal a boat like that hanging by its painter, as they call the rope, vertically, with the water below the bottom of the boat. In other words, it was hanging completely in midair. Now, that's a long time ago, and I'm sure somebody took a photograph, but it was well before the time of the internet, and they obviously haven't posted it. So if you ever see an example of that happening, take a photograph of it and put it on the internet, because that's only a sort of a half-hearted example of what can happen. But I literally saw that with my own eyes, and I thought, what do they do? Do they cut the rope and let the thing fall down into the water, or do they wait for the tide to come in again? There's an awful lot more, but I'm not going to go into it because I want to leave time for questions. The moon's motion is incredibly complex. I haven't even mentioned things like the major and the minor lunar standstills. In fact, if you read the famous Eclipse Guide by Fred Espenak, where they look at the detail of the motion of the moon, to calculate the moon's position accurately, there are approximately 37,000 elements that you need to put into your equations. Most of them relate to the longitude of the moon. I think about 14,000 of them you need to take into account to measure the longitude of the moon, about another 10,000 or so for the latitude of the moon, and another 10,000 or so. I know those don't add up, but that's approximately the ratio to the distance of the moon from the Earth. It is incredibly complicated. Now, most of those factors are very, very small, but some of them are not quite so small, and they can combine and so on. And they also add minor factors to the tides. So if you really, really want to get into the detail of the tides, you need to allow for that. There are also things like tidal surges, where the tide is amplified by a very low atmospheric pressure. And I mentioned that earlier when it happened up in Donegal. You get what's called a rip tide, where it's basically the geography of the local coastline. The tide is coming in at an angle in a bay, and the water is coming in, but some of it maybe isn't, what's the best way to put it, friction with the beach. The sand in the beach is slowing its progress, and some of it is thrust out again, and therefore you get the tide going out, and if you get caught in that, you can get swept out to the sea. There are also tides in the land. The surface of the earth is pretty solid, but it's not absolutely rigid, and you can, with sensitive enough equipment, detect tidal movements in the crust of the earth. There are smaller tides, obviously, in closed seas like the Mediterranean or the Black Sea, but even Lough Neagh, the largest lake in Ireland, has tides, although they're much too small to be measured by your average person. You need very sensitive equipment. Now, there are other things that are called, or used to be called, enemy tidal waves. They're not tidal, but they give the impression of a tide coming in, and we now call them tsunamis caused by earthquakes. And another thing, which again I don't have time to go into, but it's again becoming very important, and that is tidal energy. The energy of water moving in and out, particularly along a narrow channel, has a huge energy potential. For example, in Strangford Lough, which I mentioned earlier, they put in a trial tidal generator there, and they found out that there's enough energy there to power, excuse me, all of the energy requirements of Northern Ireland. They didn't proceed with it because of the environmental impact. It was causing damage to seals and to fish and so on, the rotating blades. But there are other ways of doing it, and there is a huge amount of energy, certainly for anywhere near the coastline. So that is something that probably will become very important in the future. So that's it, folks. Thanks for listening. And if there are any questions, I'll be glad to try and answer them. And apologies again for the hesitation at the start.
Wow, Terry, fantastic. And no need to apologize about the start. These things happen. But that was fascinating. So there's a couple of questions and a couple of comments coming in already. So we might you might want to get yourself a drink of water, because you've been non-stop for the last.
No, I'm fine. I have a drink of water here if I want it.
All right, fantastic.
As I was saying to you earlier, I don't want to dip my microphone into the water. Right, can you read out the questions, or will I try and read them?
Yeah. So the first one is coming from Mick McCreary, and he said,
"Oh, I know Mick.
Yeah, an excellent talk, Terry. And could life survive without the moon?"
Ah, yes, that's an interesting one. It could survive without the moon, but it would be a lot more hazardous. First of all, I'll go back a bit. There was a theory that life started on Earth as a result of the evolution of primitive organic molecules in the tidal zone, where they were alternately exposed to the water and then dried out and exposed to radiation from the sun and so on. That used to be one of the most popular theories for the origin of life. Now there's other ones that say that it may have been brought by comets and asteroids and so on. So that's one aspect, and it's still very much a possibility. Sort of the sludge, the tidal sludge, what we would call algae now in tidal pools, may be something similar to what early life on Earth was like, very primitive single-celled organism. But to come back to the point, the moon keeps the Earth's orbit. Even though it's so complicated, it has a stabilizing influence. There are long-term factors called Milankovitch cycles, which affect the orbit of the Earth. They affect both the ellipticity of the Earth's orbit and they affect the tilt of the Earth's pole. And both those have significant effects. And you maybe know that there have been a whole series of ice ages in the history of the Earth. The last major one ended about 10 or 12,000 years ago. And they are caused mainly by these Milankovitch cycles. The moon actually moderates those quite a bit. And to come back to Megan's point, if we didn't have the moon, the variations would be even more extreme. In other words, there'd be a much greater variation in the ellipticity of the orbit. Sometimes it would be almost circular. Sometimes it would be about twice as elliptical as it is at the moment. And also the tilt of the axis, which at the moment is 23.5 degrees. Again, that varies slightly due to nutation. I'm not going to go into that. Don't mix it up with the precession, two different things. That varies at the moment by just about half a degree over very, very long periods. But without the moon, the variation would be much greater. And that means that, to sort of sum up, that the climate variations on the Earth would be much, much greater without the moon. So we could have extreme ice ages and extreme periods of extreme heat. So that wouldn't necessarily mean the end of life on Earth, but it could make it an awful lot more difficult, particularly for sort of our species, which is more or less got used to a reasonably moderate climate. But yeah, good point. It's very much, we're 99.99% certain that that's the case. We can't measure it at the moment, but yeah, that's thought to be the case.
Brilliant. Another robust answer there. Come here. There's a couple of comments and a couple more questions, Terry, so I might just bounce them out to you there. Comments here from Fiona Hopkins. Hi, Fiona.
Hi, Fiona.
Talk, Terry, and fascinating to hear about the discovery of phosphorus on Enceladus.
Yeah.
Come here. Charles Smith. What causes us to only see one side of the moon?
It's a captured rotation.
Yeah.
The moon doesn't have any water, as far as we know, never did, or if it did, it was very, very small amounts, would have been brought to it by comets and asteroids, impacting it the way that we think the water was brought to the Earth, most of it anyway. But the moon's gravity is too small for it to have actually held on to that water. And it has no atmosphere. So any water that ever was there has simply evaporated off into space. So there are no water tides on the moon. But nevertheless, the gravitational pull of the Earth on the moon is so much that it has actually distorted the moon into an egg shape instead of being circular. And the large end, if you like, of the oblong of the egg has it's pointing towards Earth, and the pull of the Earth has gradually slowed the rotation of the moon. The moon would originally have rotated on its axis, but the Earth's pull on that bulge over the millennia, over the millions of years, over the tens of millions of years, has slowed down the rotation of the moon so that that bulge is always pointing towards the Earth. Now, as I said, it's not as simple as that, because the moon not only speeds up and slows down in its elliptical orbit, its orbit is also inclined at 5.5 degrees roughly to the ecliptic, the angle or the plane of the Earth's orbit around the sun. But the moon can't just sort of, I don't know whether you can see my hand or not, but it can't wag backwards and forwards with a period of a month. There's too much mass there, too much inertia. So sometimes the bulge is pointing slightly ahead of the direction to the Earth-Moon line and slightly behind the direction to the Earth-Moon line, or slightly above or below it, depending on the inclination of the orbit. So altogether, we can see about 59% of the surface of the moon, but only 50% at any one time. But basically, it's the gravitational pull of the Earth on the bulge that it caused on the moon that keeps the moon's face always pointing towards the Earth, with the caveat of those libration effects.
Brilliant. One more question here. So from Sue Davis, fascinating talk, thank you. Does the gravitational pull of the sun and the moon cause the tectonic plate movement? Ah,
right. There is a very slight effect, and it would be mainly the effect from the moon, because, as I say, it's much stronger. But no, most of the tectonic effects on the Earth are caused by the internal workings of the Earth itself. Now, I'm not a geophysicist, but basically the Earth has a solid core, even though it's very, very high temperature, a mixture of iron and nickel. Above that is what's called the mantle. Sorry, the core is, off the top of my head, say 1,000 kilometers diameter, roughly, ballpark figure. Outside that, you have what's called the mantle, which is semi-liquid molten rock. It's not, it doesn't run free, it's sort of like treacle, if you like. Above that is what's called the upper mantle, which is the part immediately below the crust. And that's where the molten rock comes up to the surface when you have a volcanic eruption. So what is happening, and we don't entirely understand this, a lot of the heat in the internal of the Earth, and you know, obviously, that the inside of the Earth is much hotter than the outside. That's why you have molten lava when it comes out at several hundred degrees, or the hot smokers at the bottom of the oceans, again, temperature of several hundred degrees, sometimes more. There is a lot of heat down there. Part of that is the original kinetic energy of all the impacts that formed the Earth in the first place. Whenever two large bodies collide with each other, there's a huge release of energy, and a lot of that is in the form of heat, and that gradually sort of accumulated. But at the moment, most of the heat in the interior of the Earth is caused by radioactive decay of the elements that are in there. And again, not a geophysicist, but uranium, thorium, plutonium, whatever, radium. So they are slowly decaying to other products, giving off heat in the meantime. So the net result of that is, apart from the solid core, the mantle around it is full of heat being given off by this radioactive decay. And that causes basically motion of the mantle, a bit like the effect, obviously a lot slower, but a bit like the effect of watching water boiling in a saucepan, where you get up currents and down currents. The water boils up towards the surface, and it then descends again. Maybe a better example would be a bowl of porridge or a bowl of soup, where you can see it more easily. Now, that's happening on an incredibly slow time scale, but nevertheless, that's what's happening. So where two tectonic plates are moving apart, as happens, for example, in the mid-Atlantic ridge, there's a source of heat underneath there, which is rising up to the surface, and it is forcing the two tectonic plates apart. The North American plate and the European plate are moving apart at roughly the rate that your fingernails grow. And Iceland sits exactly on that mid-Atlantic ridge, and that's why there's so much volcanic activity on Iceland. And of course, those plates have to go somewhere. So at the other end, the plates collide with another plate, and something has to give. One of two things will happen. Either the edges will move upwards and you get a mountain ridge like the Andes or the Rockies, or one goes down onto the other. It's called subduction. And that's where you get a lot of earthquakes. So the plates are continually moving very, very slowly over the surface of the Earth, but it's due to this extremely slow motion convection currents in the mantle, and the heat source for that is mainly radioactive decay. I hope that answers the question.
It's a very, again, another good answer, Terry. I'm just going through, there's a few more comments coming in, and a couple more questions here. So Lisa Buckley has Lisa, would you like to ask that question directly? And we can stop the recording if you